and go from the current slide. All right. Can't think if there are any announcements for today, except if you haven't voted yet, please vote. Today's the day. Please vote. Get into the habit of voting every time those polls are open. And you got until 7 this evening to vote. Okay? I voted already, but I forgot to get a sticker. I almost turned around and went back in the building. I said, no, I can't do that. I got to get it work. So, Anyway, there's, I can't think of any, let me say this. All of your papers are graded. They're not on Blackboard yet. I'm getting closer to getting that done. I still have a few more to grade here, but as soon as I get those done, yesterday was a successful day in grading. Not as many as I would like to have, but Amanda's here. But at least I got through one complete lab in that big class that I've got and got started on the test, so that was good. Today, hopefully, I'll be able to make good progress on the rest of it. The schedule for spring for the math part is finally finished. I finished just about everything on Friday. Thought I had it all finished. I thought it was another couple things I needed to do. Got those done yesterday. So finally that's done so I can get back to grading. And once I get it graded, then get things in Blackboard and maybe get my head above water again. Then I still have summer scheduled to do, but that's, I'm going to kick that can down the road. Okay. But anyway, hopefully you'll see things start catching up as I start catching up. All right, any questions on anything we've done so far? Now, if my memory's right, and it seldom is, my wife tells me anyway, we did example 3 last time, not realizing we had skipped example 2. Okay, so we're going to do example 2, even though example 3 is on the slide here, but we're going to go with example 2. Find, if possible, the rational zeros of f of x is equal to x cubed plus x plus 1. Okay? Now, remember how we did rational zeros? No, it was a long time ago, at least 5 days, that we did this. What was our procedure for rational zeros? Well, rational means ratio, P over Q. What in the world is the P? Oh, a long time ago. Factor of the constant. All the possible factors of the constant term, which is 1, so that's plus or minus 1, and the Q is? Yes, it's all the possible factors of the leading coefficient, which is 1. So what are our only 2 options for rational zeros on this problem? Yes, plus 1 and minus 1. Now, plus 1 is real easy to do, right? Add your coefficients, okay? And when you add those coefficients, what do you get? 3. That's not 0. So 1 is not a 0. So the minus 1, the easiest way in my mind to do it is you could plug it in just like we did there, though you didn't realize we plugged it in. But I think it's easier to do synthetic division. So I put minus 1 on the outside because that's the 0 we're investigating. What do I put on the right-hand side? 1, 0, excellent. 1, 1. Skip a line, draw a line. Bring down the 1 and start to work. What does that give you? Negative 1, negative 1, positive 1, 2, negative 2, negative 1. There are no rational zeros. Come on in, just because the buzzer went off. Hill? Okay, good. Alexis. All right, good deal. All right. There are no rational zeros for this problem. Now, I don't mean to mislead you in any way, but so many times in the text, if they say, if possible, that's a good indication there may not be any. Okay? Because if there are some, they'll probably not say, if possible. But that's not always the case. But in this case, it certainly was. There are no rational zeros. So what you have to do is then do some of the techniques like we did before. For instance, f of 0 was 1, and f of minus 1 is negative 1. Remember the remainder test, the remainder theorem? So you know it's between 0 and negative 1. That's all we know. They show that in the text. I can't project it here because they don't do it, but there is no rational zero for this problem. That 1 0 that you see there must be an irrational number. Okay. The other two, because there are 3 zeros, right? Fundamental theorem of algebra, that kind of stuff. The other two have to be complex, imaginary parts. So we're not even going there either. So that's really all we can do with that one. There is a checkpoint, and please take a look at the checkpoint. Now, even if we hadn't determined that at x equals 0, the function was plus 1, and at x equals negative 1, the function was negative 1, even if we hadn't determined that, before we even started, could you have looked at that function and told me there is one real zero? Anybody? How? Why?
Plug in 0.
What's that?
Like I would have just plugged in 0 to it.
Yeah, but that's not a 0, okay? We want the place where this is equal to 0. And I can guarantee you there is at least one location where it is equal to 0. Why can I guarantee that? Just looking at this without doing anything else. Hint, hint. So again, it's a cubic polynomial. In other words, its degree is odd, which means what? The end behavior is 1 negative, 1 positive, one or the other, okay? One or the other, because it's odd. And guess what? If you go from negative infinity to positive infinity, you got it, because this is a polynomial function, which means it's two features. The curve is smooth and continuous. So if it's smooth and continuous, and what starts at negative infinity, ends at positive infinity, or vice versa, it has to cross x equals 0. I mean, y is equal to 0 somewhere. Has to. There's no way it can't jump over it because it's smooth and continuous. So I could guarantee you that has at least one real 0. It could have 3, but it has at least 1. And the figure in the book shows you it does. It's just not a rational 0. It's a irrational 0. The other two happen to be complex. All right. We did example 3, right? So let's move on past example 3. Y'all remember doing it, right? Okay. And here is continuing with the rational 0 test. When the leading coefficient of a polynomial is not 1, that means that some of those denominators may not be 1. They could be rational numbers, fractional forms. So the list of possible rational zeros can increase dramatically. Okay? In fact, for every possible factor of that denominator, each one of them doubles, well, or something like that, the number of possibilities. In such cases, the search can be shortened in several ways. So here's one. Cheating. A programmable calculator used to speed up the calculations. Yeah, okay. Okay. A graph drawn either by hand or with a graphing utility can give a good estimate of the location of zeros and tell you about how many there would be, as long as you have the scale big enough. If you have the scale too narrow, it may only look like 1 or 2, but if you widen it out, you might say, oh, it crosses again here and here. Okay. So there are some other things. And the intermediate value theorem, along with a table generated by a graphing utility, can give approximation to 0. My goodness, all that requires programmable calculators. Guess what, folks? We can get by without them. But if you have them, use them. They're good. Okay? There must be more because it ends with a semicolon. Here's number 4. Synthetic division can be used to test the possible zeros. That's the one we can do. Enjoy doing it, right? Synthetic division is fun. Finding the first 0 is often the most difficult part. After that, the search is simplified by working with the lower degree quotient rather than the higher degree dividend that you started with. Okay? And we did that in example 3. Recall that if x equal a is a 0 of the polynomial function f, okay, then x equal a is a solution for this polynomial equation, f of x equals 0. That's what it means to be a 0, to be a solution, to be a 0. It's also, what else can you tell me about that? 2 other features. If you know that x equal a is a 0, also a solution of the polynomial equation, what other 2 things can you tell me about just knowing that fact? See, people at home don't get to see this. You get the hints. Okay? Really helpful, weren't they? Okay. Not that funny. Okay. All right. What if we subtracted the a from both sides? X minus a would then be a factor of this polynomial f of x. Okay? And one more. The point on the graph, a comma 0 would be the a and intercept, an x-intercept. Okay, an x-intercept for that polynomial function. All right, we got those, don't we? Okay. That was the bottom of page 154, and they skip, they skip example 4 and 5. So let's go back and do 4 and 5. We'll do it on 3 again. Okay. Find the rational zeros of f of x is equal to 2x cubed plus 3x squared minus 8x plus 3 plus 3. Stop. Okay. Now, where would you begin? Looking for rational zeros again. So where would you begin? The zeros will, if they have any, if possible, will be of the form p over q. And what are your possible p's? P's porridge hot? Possible p's. It's been 10 minutes. How easy to forget. Positive, negative what? 1, of course. Plus or minus 1. Plus or minus 3. All the possible factors of that constant term. And that's all, folks. Okay, how about the denominator, q? Plus or minus 1. Okay, positive, negative 2. Okay, now what I like to do is list them out now. That gives us all the possibility. Now I like to list them. And over the plus or minus 1, we can just do plus or minus 1, plus or minus 3. Now, the book doesn't do them that way because it does from small to large. Guess what? I like to get rid of my constants first, then get to the fractions. Whole numbers first, then get to the fractions. Those are the first two when you put the numerator over the plus or minus 1. What are the next ones? And you put the numerator over plus or minus 2. 1/2 or 3/2. Okay. Now, which is the easiest one to start? 1. Okay, and what do we do with 1? You don't even have to with 1 yet. Remember, 1 is so easy. What you do is, because if you put a 1 here, that's 1, 1, and 1, okay? So all you have is your coefficients, right? Add them up. 2 and 3 are 5, minus 8 is, plus 3 is 0. We've just found the 0. X equal 1 is a 0. Now, we're going to do exactly what you said. We're going to use synthetic division using that, but we know that 1 is. If that didn't add up to 0, we wouldn't even mess with 1, okay? And what do we put inside or on the right? 2, 3, -8, and 3, okay? Now, sometimes I just go and write those down because those are your coefficients. That's going to be what you're adding up, so I just do that, okay? But you did it in your heads, that's fine. Skip a line, draw a line. Bring down the 2. 2, 5, 5, -3, -3. We're not at all surprised, are we? We knew that was going to be a 0, but we've just done it. And guess what we do now? What do we do now? Yes, this represents a quadratic. 3 terms. Squared, linear, constant. So yeah, we can factor that. If we can't factor it, we can quadratic formula. Exactly. Okay. So let's see if what does that represent then? 2x squared plus 5x minus 3. Can we factor that baby? And we set it equals 0 because we're looking for the zeros, right? Where do we begin? With the 2, only possible factorizations of 2x squared is x and 2x. Perfect. And then where do we look next? Sign of the last term is negative. That means these two signs have to be different. Which way you want to list them? Minus first and plus second. Okay, we'll try it. Okay, and what's the possible factorizations for 3? 1 and 3. Is that the way you want to do it? All right, may work. Let's check it and see. FOIL it. X times 2x is 2x squared. That works. X times plus 3 is plus 3x minus 2x. Nope, doesn't work. All right. Yes, wrong number, so change numbers. Exactly. Okay. So we'll make this the, what was that? 3, and this the 1. Okay, let's try it again. X times 2x, 2x squared. Yeah, that still works. Then you have plus x. All right, here's Cameron. Just woke up from the storm, right? Okay. All right. Good deal. Anyone else come in since I called that? Okay. What does the inner give you? Negative 6x plus x is? So close. But the sign's wrong. The number's right, but the sign's wrong, so what do we do? Swap the signs. Okay. So I can't get that to erase. I don't need to erase it, but we'll make this the minus and make the other one the plus. Okay, let's try it again. X times 2x is 2x squared. That's still right. Then we have a minus x plus 6x. That gives us our plus 5x and a minus 3. And we are a happy face now because that does work. Okay? That gives us our other factors. Okay? We really didn't want the other factors. Okay? I should have done this. X equal 1, that's the 0. That's what we're looking for. We've got two other factors, and we could set these equal to 0. How do we find the zeros? Set each of them equals 0. So this implies that either x plus 3 is equal to 0, or 2x minus 1 is equal to 0. And what does the first one tell us? X equal negative 3. And looky here. There is a possible rational 0. It was one of our possibilities. What does the other one tell us? Yes, x equal 1/2. When you add 1 to both sides, divide by 2, Dimitri comes in. Okay? It happens every time. Okay. All right. Good deal. Anyone else come in since I called roll? All right, and just look right there. There is a plus 1/2. That was also a possible rational 0. Yes. We had 8 possibilities. We knew we could have up to 3 solutions. We have 3. The plus 1, the minus 3, and the positive 1/2. Okay? Now, they said, yes?
So I got kind of lost on how you got the possible rational zeros.
Okay. All right. What we do, because they're rational, set up a ratio, P over Q. What goes into the P? All the possible factors of your constant term, 3. That's plus or minus 1 and plus or minus 3. Okay? What goes into the Q? All the possible factors of your leading coefficient, plus or minus 1 and plus or minus 2. Okay? And then from there, we start laying them out. Okay? With that plus or minus 1, you just use the numerators, plus or minus 1 and plus or minus 3. With plus or minus 2, you use the denominators over that. That would be plus or minus 1/2 and plus or minus 3/2. 8 possibilities. Now, one thing to remember, especially if this is a big, long, hairy, high-order one, remember you can have repeated zeros. So this one, after that first one that worked, we were down to a quadratic automatically. And that was easy to do, okay, relatively. If we had still had a 4th or 5th degree polynomial to do then, what we would have to do then is keep trying. But don't forget that that first one could be a repeated 0. So you have to try it again until it doesn't work and then go to another one. So that's the one thing I tend to forget is I could have repeated zeros. Just like Ron could be here, but you know. All right, he is. All right, good deal. Anyone else come in since the call roll? So there we found all the possible rational zeros of that polynomial. Okay. Ready for example 5? Sure we are, okay. With much enthusiasm. Okay. We'll do example 5. Find all the real zeros of negative 10x cubed plus 15x squared plus 16x minus 12 equals 0. Here it says find all the real solutions. Guess what? The real solutions of that are the same as the real zeros of a polynomial, right? Without the equal 0 in there. The function is the first part. Okay. Now, where would you begin? First thing you think of when you look at that.
You have to do the P and Q.
Say again?
You have to do the same thing.
Yes, we do. But what I think of when I see that, is there anything I can do to make that simpler? Okay? Because those are big old numbers there. Well, let's think about it. This has factors of 2 and 5. This has factors of 3 and 5. Well, 5 is a possibility. This is 2 and 2 and 2 and 2. Nope. Not going to work. Okay? Because there aren't any common factors. Shucks. Okay? But always try. Always try to make it as simple as possible. Now, the other thing I kind of don't like is starting off with a minus sign. But there's nothing wrong with it. I just don't like it. But we'll keep it. There's no reason to change. But we could have if we had wanted to. Now, where do we go next? And this is what Christian was trying to get me to do to begin with.
Look at the last term.
Okay, we're looking for a rational expression, P over Q, where P is, ooh boy, all the possible factors of 12. And what would that be? You gonna give up sometime here? Okay. 6. And whew, goodness gracious. We're gonna be here all day, aren't we? Okay. Next.
We gotta look at the leading coefficient.
Okay, and what will that give us?
Plus or minus 1.
Wow. Okay. There's 2, 4, 6, 8, 10, 12 times 4. 48 possible rational zeros. Can you hardly wait to start finding them? Okay. We got our work cut out. Now what I like to do is start listing them. Okay? Not always fun, but here, let's do it. If you do over 1, it's just your numerator. So it's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Okay? Now let's start doing each one of them over each of the denominators. What's next? Plus or minus 1/2, plus or minus 2/2. Well, guess what? That's 1. At least we got rid of 1. Okay, then plus or minus 3/2. You don't have to list them again, okay? And 4/2 is 2. We've already listed that one. Then 6/2 is 3. We've already listed that one. And 12/2 is 6. Ha! We've eliminated a few anyway. Go to the next one, and what do you have? 1/5 plus or minus 2/5 plus or minus, keep going, 3/5 plus or minus 4/5 plus or minus 6/5 and plus or minus 12/5. Not much help there, is there? Okay. Next. Plus or minus 1/10. Plus or minus. Yeah, but we already got that one, don't we? Whew, good. Okay. And 3/10. 4/10 would be 2/5. We already have that one. 6/10 would be 3/5. We already have that one. And 12/10 would be 6/5. We already have that one. Whew. Finally, we're through with those. The good news is you're never going to have to go through them all, I don't think. I've never had to yet. Where do we start? The easiest one. Plus 1. Okay? And what's the easiest way to do that?
Just add up the coefficients.
Add your coefficients. I'm going to add the negatives first. What does that give you? Negative 22. Oh boy, calculators are slow, aren't you? Grind. 31 plus 31. Not going to be a 0. Good try, but that means we don't even have to try with plus 1. So at this point, I'm going to try, well, I'm going to mark JT present first. Okay? All right. Anyone else come in since I called roll? Okay, I don't have a lot of room, so let's start trying. We're going to try, which one you want to do next? It's up to you. -1. Okay, let's do -1. Okay, and what goes inside? -10, 15, 16, -12. Okay, now I've forgotten to say this. I usually like to say it every time. Is that enough numbers for synthetic division? Yes, it's always one more than your degree. Degree is 3, this is 4. Yes. So what do we do first? After we draw a line, skip a line, draw a line. Bring down the -10. +10, 25, -25, -9. Okay. Now I'm going to cheat a little bit here. Okay? I'm going to tell you something we're going to run into later. It may be helpful here, it may not be. When you're doing a negative number into this and you look at your answers down here, if they alternate sign, every one of them, then you know you can't go any lower than that negative number. Okay? It's called the lower bound test. We haven't gotten there. We're not alternating yet, so we keep trucking. Okay? Or at least we keep trucking after I get Ryan marked here. Okay? There you are. Does anyone else come in since I called roll? Okay. So, -1 won't work. +1 won't work, so both of these are out. All right. So I'm going to erase that. Oops, I didn't need to erase. That what?
Didn't you say that, like, sometimes you have to do it again with the same one?
Yeah, but if it didn't work the first time, it's not going to work again. Okay. The -10 I could have left there. I botched up and erased too much. I can't write. Erase it all and write it again. Okay. All right. So what? +2. We have a suggestion for +2. Let's go with that. What does that give you? -20, -5, -10, +6, +12. Ding, ding, ding. We got a 0. Okay? And guess where we are now? Yeah, we can factor that, or we hope we can anyway. So we're down to a quadratic. Okay? And that quadratic is -10x squared minus 5x plus 6 equals 0. Okay? Now, at this point, folks, I really don't like that leading negative number. Okay? So guess what I'm going to do, and it's legal in almost every state. Okay? I'm going to multiply everything by -1. Both sides. Okay? Doesn't change anything. There'll be a plus, this will be a minus. Oops, too much ran out. Okay? And that is a -0 now. Okay? It's still 0. Okay? So, let's see if we can factor that. Okay? We still got a pretty big, a lot of choices, let me put it that way. Okay? Now, does anyone remember a little technique that might be helpful when you have a lot of choices and you don't want to do trial and error? Quadratic formula? He loves that quadratic formula. He answers it every time. Yeah, you can do that. You certainly can. There is another technique, though, called the AC test. Have y'all ever heard of that? Huh? Okay. Here's the AC test. Sometimes it takes a while. It might, but okay. Remember when we wrote this ax squared plus bx plus c? So a was 10, b was 5, and c was minus 6. So AC in this case is minus 60. Now that's a big number, okay? And what we're going to look for is possible factors for minus 60 that add to b, and the b is positive 5, okay? Now, what we do here, and I like to do as much as I can to eliminate as much work as possible because I'm lazy, okay? And here's what I'd say. If AC is minus, that means, okay, what we're looking for, okay, I left this part out. We're looking for two numbers, M and N. Why they keep throwing these letters in there, I don't know. M and N, that the product of this is minus 60 and the sum of that is 5. Well, if the product is negative, that means one of these is positive and one's negative, right? Which one's the bigger number? The what? Positive or negative? Positive, because B wins, okay? Number 5, 5 is a positive number. So I'm only going to put my small numbers to be negative, large numbers positive. Now I'm going to start, even though I know it's not going to work, I'm going to start with the very basics. The first one of those would be, I'm going to move that out of the way. Again, this is awfully crowded board here. Okay. I'll put the M and N out here, okay? That could be a minus 1 and 60. No way that's going to add to be plus 5, though, is it? It's going to be positive 59, right? Not work. What's the next one? Negative 2 and 58. That adds to be 56. It's a little closer, but we got a long ways to go, don't we? Next one, negative 3 and... Oh, I've messed that up badly. That was 30. Negative 2 times 30 is negative 60.
I was like, wait, what happened?
Okay, and that would be... Sorry about that, folks. I'm off to lunch here somewhere. Okay, let's get that one right. Negative 2 times 30, so that would be a 28. That's a lot closer than 59, but it's still not close enough. Okay, so negative 3 and negative 3 will go to negative 60. Help me, folks. 20, and those add to be 17. That's closer yet, but still not good enough. And here's Ashley. Okay. All right. What's the next one? Negative 4 and? Help me, folks. 15. What does those add to? Positive 11. Positive 11. Okay. Well, that's closer to 5, but still not there. All right, I'm running out of room. I'm going to pull it over here. Next is going to be negative 5 and somebody, 12, and that adds to be 7. Oh, so close, but not there. How about negative 6 and 10? Uh-oh, I messed up something there, didn't I? That adds to 4? Have I messed something up here? This was example 5. Oh, you were right all along. You knew that, didn't you? Okay. But this was still something worth doing, because you see, when we got here, And negative 512 gave us plus 7. Negative 610 gave us plus 4. We skipped right over our target, 5. So there is no other rational number that's going to be that. Okay? So therefore, we've got to use your favorite. Okay, you knew it, didn't you? Okay? The quadratic formula. Okay. So sorry about that, folks. But guess what? We still need our A, B, and C, don't we? Okay. So let me do some erasing here. Okay. All right. We're asking real solutions. So one real solution, before I erase it, is going to be x equal 2. That was a solution. We got that one. Then we got down here. So what we're going to do, and guess what? X equal 2. That's going to be our only rational 0. We just ran out when we skipped that 5 there. We don't have any more. So therefore, let's erase just about everything else we got here. I'm going to keep that. I'm going to erase that and that, that and that and that. And all this scratch. It was worth the effort, folks, but it produced nothing. Okay? Full of sound and fury, signifying nothing. Okay? All right. So, quadratic formula, how does that go? Anybody? Okay, x equal minus b plus or minus the square root of b squared minus 4ac all divided by 2a. And that's where we need our a, b, and c. Okay? Even in this change form, it still is going to work okay. So, what do we have here? What's your b? 5, so negative b would be negative 5 plus or minus the square root of 5 squared, which is 25, minus 4 times a is 10 times c is negative 6. Okay? All over 2 times 10. Now, if you left it in the other form, yeah, the signs are changed, but everything works out the same. Okay? Now, what we do here, to start, this is going to be, I don't have much room, minus 5 plus or minus the square root of 25. Okay? Stop there. Stop there, too. Okay. Now, what I do next is this is always a minus 4. So there's always one minus sign. These two are opposite signs, but you count your negatives. Plus and plus, minus times minus is plus. So that sign here is going to be a plus, which guarantees you that we're going to have an irrational 0. Okay? It may be still if that was a minus, but if that's a plus, you definitely do. And then you multiply those together, and what does that give you? 4 times 10 times negative 6. Or forget the signs. We already got the sign in place. It's what? 240. One of my favorite numbers. Okay. I'm just kidding. Okay. Divided by 20. Okay. 2 times 10. Okay. Now, this is awkward from here, but I think I can do it. I don't have enough room. I'm going to move up here. Minus 5 plus or minus the square root of, what's 25 plus 240? 265 divided by 20. All right. Now the next thing we usually want to do, see if we can find any perfect squares hiding in that. And I'm not sure there are. Let's see. I know 4 is not in there. 11 and 2 and 13, so 9's not in there. 25's not in there. 16's not in there. 36 is not in there. 49, I don't think so, but someone do that. See if 265 is divisible by 49. I don't think it is. Is it? I'm pretty sure it's not. I'm certain it's not. Okay.
It's not.
Say again?
It's not.
It's not. Okay, then after that, 64 is not divisible there, and 81 I'm pretty sure isn't, because 9 isn't. So the next one would be 100 isn't. And I think we're getting too big. So yeah, that doesn't, there's no perfect squares in there. So that's our answer right there. Those are the other two zeros. The first of these is, I wish I had written that somewhere else. Okay. I'll get by with this. Okay, let me get. Okay, is it Trees? Okay. Gotta find you. There you are. Now, did someone else come in while my back was turned? Didn't mark you down? I think I got it all. I don't see anybody else. Okay. So, the first is x equals 0. The next one is minus 5 plus or, no, I'm sorry. Yuck. I'm so used to writing plus or minus. Minus 5 plus the square root of 265 over 20. And then the second one, I'll erase this now. Okay, is that one. Okay, that was cheap, wasn't it? The second one is minus 5 minus the square root of 265 over 20. Pretty big, hairy, miserable numbers. One of those is negative 1.0639, blah, 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 blah. They're irrational, so they go on forever with no pattern. The other is positive 0.5639, blah, 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 blah. Okay. And then they do show in your graph there, which the PowerPoint doesn't show if you got your book, your text. X equal 2 is a 0. You see that one. The other two, the positive one is just past 0.5, and the other one is over there beyond negative 1, just past negative 1 on the left of it, negative 1.06. So 2 irrational zeros, yes.
Do you want us to write it like that or as a decimal?
I prefer it like that. That's exact. Okay, but if you write in decimal, I can handle that too. Okay. Most of the time I've got a calculator nearby. I'll check. So, yep, that's right. Okay. Now, any questions on that? Now let me say this. I believe it's just about always true. Whenever you have these irrational solutions, they're just about always going to come out as, what do we call these? Say again? They're irrational, but one's plus and one's minus. Conjugate pairs, exactly. They're irrational conjugate pairs. The next thing we're going to talk about are complex conjugate pairs. And these answers just about always come out with that. There are exceptions to that, and we'll talk about those as we get to them. Okay? So, any questions on example 5? Not a very pretty answer, but definitely an answer. 3 real zeros, only one of them's rational, 2 of them irrational, and they're conjugate pairs of each other. All right, with that done then, if there are no questions, we'll move on to conjugate pairs, okay? These are almost as good as Bartlett's, but not quite. Okay, but no. Conjugate pairs are, note that when the pair of complex zeros are conjugates. What are they talking about here? Okay. There was a statement at the beginning that they sort of skipped over here. They said in example 1C, and that was way back, okay? Way back at 1, you had two zeros on number C, 1C. You had x equals 0, x equal 2i, and x equal minus 2i. Well, those are conjugate pairs of each other, okay? That's what the note is about. They just left off the first sentence, you know, that said in example 1C, note that the two complex zeros, 2i and minus 2i's, are complex conjugates, okay? And now it says, note that the pair are conjugates. That is, they form a plus bi and a minus bi. Just like the one we just did had irrational conjugate pairs, okay? So, here's the deal. If f is a polynomial function that has real coefficients, okay, now what do we mean by real coefficients? They could be positive or negative, fractions or decimals, irrational or rational, any real coefficient, then if a plus bi is a solution where b is not equal to 0, so it does have an imaginary component, then is a 0 of the function, then automatically a minus bi is as well, okay? And it's also a 0 of the function. And guess what? We're only going to deal with real coefficients. If you had complex coefficients, like you had x squared plus 2ix plus 7, okay, and you tried to do something with that, yeah, you may only wind up with one complex solution. You wouldn't have to have a conjugate pair. But if all those are real coefficients, then the complex, if you have complex roots, they always show up in pairs. So let's step back one to our last problem. If we have only rational coefficients, then your irrational solutions are going to be in conjugate pairs too. If you had an irrational coefficient, then yeah, you may not. So that's why I said they don't always go up in conjugate pairs, but as long as that condition is met. Be sure you see that the result is true only when the polynomial function has real coefficients. That's the only ones we're going to worry with. For instance, the result applies to the function f of x equal x squared plus 1, but it doesn't apply to the function g of x is equal to x minus I, because that only has one solution, x equal I, not the conjugate pair. Okay, so all the coefficients have to be real numbers. Okay. Got it? I'll leave it up there a little longer if y'all are still writing. Okay. So we move on to example 6. Now, guess what? I'm going to try not to give you complex problems because that's really not under the course description of this course. But since the book is covering it, I'll go over this, but let's do it quickly. Find a fourth degree polynomial function with real coefficients that has -1, and 3i as zeros. How would you do that? You're now not given a polynomial function finding the zeros. This time they're giving you the zeros and say find the polynomial function. So how are we going to do this? All right, the factors of this are x plus 1 times x plus 1. Go on, you got a good start there. X minus 3i. And then what we just discovered. If they have real coefficients, and it says it will, if 3i is a 0, what else has to be a 0? -3i, the complex coefficient, conjugate of that, which would be 0 minus 3i. So then its factor would be x plus 3i. Okay. Now, you could, if you're really absolutely incredibly lazy, say, there it is. There's a fourth degree polynomial function. I just haven't multiplied it through for you. I want you to do that for me, okay? I won't appreciate that very much. but that is a fourth degree polynomial. Notice that x times x times x times x will give you x to the fourth. They really want you to multiply it out. And when you do this, remember it's very easy to multiply the two complex conjugates by each other. What does that give you? X squared plus 9. Perfect. Okay. Then it's pretty easy to multiply those two together too. What does that give you? Okay. And then it's not quite as easy, but still not bad to multiply those two together. And how you do this is just like you multiply any numbers together. Multiply each term by each term. So let's do first by first. That would give you, I'm going to take out that parentheses. I don't need it. Okay, what would first times first give you? X to the fourth. Okay. Then I'm going to do, I'm not going to follow the order as well. Second time first, that would give you 2x cubed. And then I'm going to do this squared times 9, and that would be plus 9x squared. And I'm going to do this squared times 1 plus x squared. Okay. And what have I not done yet? I haven't done 2x times 9. What would that give us? 18x. And then I think all I have left is the constant terms, plus 9. Okay, now the reason I did it that way to get it in decreasing order of the power. Most of the time I'm not that disorganized with it, but this one came out easier to do that way. And what does that produce? X to the fourth plus 2x cubed plus 10x squared plus 18x plus 9. No. Now, you could also multiply that by any constant a. Okay? That would still work. Just when you factored out the a, you throw it away. Okay? But any constant a would work too. So, let's just take a equal 1 and make it easy. Just that function there. Okay. Let's see how the book did it. Oh, we get to see how the book did it. Can I erase this? Everybody see what we did? Okay. So let's see how they proceed. They start with this observation. Because you know that 3i is a 0, they told us that. And they also told us that the polynomial is stated to have real coefficients. Then you know the conjugate of 3i, which is minus 3i, must also be a 0. We got a fourth degree polynomial, 4 0. That's all it can have. So we have our 4 zeros. Translate those to factors, which will be an x plus 1 times x plus 1 times x minus 3i times x plus 3i. And then they put the a out in front too. It's fine. You didn't have to. You could wait till the end and do that. But then what they did was pretty, for simplicity, let a equal 1. Okay, that's what we did. Okay. And then when you multiply those together, the first two, you get x squared plus 2x plus 1, just like you did. And when you multiply the complex conjugates together, those are really easy too, x squared plus 9. Then when you multiply those two together, you get that. And they didn't show all the gory detail, but that's the same thing we got. Right? Any questions? You found it. One of an infinite number. Multiply any constant by that, and you got another one. All right. They are skipping example 7. Okay? Now, one thing, folks, I forgot to bring my watch in today, so y'all have to let me know. How are we doing? 13 minutes. Wonderful. Okay, so let's back up. And yes, question? All right. Let's do example 7. Find the cubic polynomial f with real coefficients that has 2, 1 minus I as zeros. And they also tell us that f of 1 is 3. Ooh! F of 1 is equal to 3. So we're on a cubic polynomial with real with real coefficients, and those are two of its zeros. Now, how many zeros could a cubic polynomial have? 3. So we don't have them all, or do we? If they're real coefficients, what's another 0? 1 plus I. There we have it. All right, now what we need to do is find the possible, now let's find the factors. What would be the factors corresponding to those 3 zeros? First factor, x minus 2. Second factor, x, x minus 1 minus I, and x minus 1 plus I. They're a little awkward here when you have real and complex parts to them. So what you have to do with these, this would be x minus 1 plus I, and this would be x minus 1 minus I. Okay. You have to kind of do that. Now, again, it's not too bad if you here's the deal. Now that they look like that, let's group the first two together, and now they're easier to multiply, right? You have a product of two binomials is the first square, and the other one is just plus 1. Okay? So this would be, when you multiply those two together, you have x minus 1 times x minus 1, which is x minus 1 times x minus 1. X squared minus 2x, right? One last term. One last term. Help me. One last term. Plus 1. Okay. All right. Then you add those two, multiply those two, minus I times plus I, and that gives you minus I squared, which is plus 1. Right? So this gives you x squared minus 2x plus 2. That's those two. Multiply that by x minus 2. Okay? Let me go up here and do it. Again, let's do the cubic terms. That would be x cubed. Let's do the squared terms. That would be minus 2x squared and a minus 2x squared from there. And then the linear got it? Okay. The linear terms would be plus 2x and minus 4x, right? Doesn't matter where you put them. And then the constant term will be minus 4. Okay. Here's the deal, folks. When you do this, you got a 3 by 2. That gives you 6 terms. 1, 2, 3, 4, 5, 6. Yeah. As long as you got that many, you're okay. All right. So this will be x cubed minus 4x squared minus 2x minus 4. That's your cubic polynomial times some a. Okay, that's your f of x. But we also know that f, yes? Of course. You want me to do all the work? No. You do the work. I grade you on your work. Yeah. You mean you? I should never have said this is. Oh no! I knew somebody who was going to say, "Oh, I'll just leave it like that then." Won't I? No, that's not. That's most. No, actually, I'm not going to give you any with complex things. I'm going to try not anyway. And by the way, it won't be the quiz; it'll be the test because we already had the quiz. Does everybody have a copy of the quiz, by the way, for this chapter? I gave it a while back, right? Okay. All right. Those should be coming in. Remember? Yeah, yes. Okay. So yeah, but do go on and multiply them together. You can do them more organized than I'm doing them if you want to. It actually works a little bit better, but since I have such little board space, I wanted to try to condense it. All right, but here's the last part of the problem. We know that f of 1 is equal to 3. So when we plug a 1 in there, we have f of 1. And when we plug that in, we got the a here, and that'd be 1 minus 4 minus 2 minus 4. So that's 1 minus 10 would be a minus 9, wouldn't it? Okay, and that's equal to 3. Well, divide that, a would be equal to negative 1/3. So that, I hope, is the answer. No, a is negative 3. How did I botch that up? Okay, a cubed minus 4. Oh, that's a plus 6. That's how I messed it up. That must have been a plus 4x there. Plus 6. Okay, sorry about that. So now when you plug that in, you get 7 minus 1. That would be a minus 1. So this would be a minus 1 there. And that's equal to 3. So a is equal to negative 3. A is equal to, negative a is equal to 3. So a is equal to a negative 3. Sorry. That's ugly, ugly, ugly. Don't worry, y'all are not going to have to do one of those, but that's how you would work it out. Sorry, I got off. Okay. Okay. But in case you ever will in the future, that's how you go about doing those. Let's move now to how much time we got. Say again? 5 minutes. Okay. Let's get going on factoring a polynomial. As if we haven't been doing that already, okay? The linear factorization theorem shows that you can write any nth degree polynomial as a product of n linear factors. Remember, you have that coefficient out front, a sub n. I can't think of any reason to call it a sub n, but you can. Well, yes, I can. Because when you multiply all those x's together, you have x to the nth. And then that would be the coefficient for it. So that's why. However, this result includes the possibility that some of the values of c could be complex. Okay? Now, the following theorem states that even if you do not want to get involved with complex fractions, which we typically don't want to, okay, you can still write f of x as a product of linear and or quadratic factors. And why is that? Because how are your complex numbers always going to come out? Conjugate pairs. They will be complex, excellent. But complex conjugate pairs. And when you multiply those together, you get quadratics. So all those can be expressed as quadratic factors, and then the ones that are not complex can be expressed as linear factors. So here is the thing. Factors of polynomial. For every polynomial degree n greater than 0, that's n equal 1 even, with real coefficients can be written as a product of linear and quadratic factors with real coefficients where the quadratic factors have no real zeros. In other words, those contain your complex parts, and they always show up as complex conjugate pairs. Okay. So, a quadratic factor with no real zeros is said to be prime or irreducible over the reals. I don't like that term too much, but that's what they call it, irreducible over the reals. You can't factor it any further, not with real numbers. Okay? Note that this is not the same as being irreducible over the rationals. That was like the one we did before. That wouldn't factor. It was irreducible over the rationals. For example, the quadratic x squared plus 1, no way you're going to factor that with real numbers. With complex numbers, yes, but not with real numbers. That's irreducible over the reals, therefore over the rational numbers. We've been saying that from the beginning. No factors. Impossible to factor using real numbers. Okay? On the other hand, this quadratic here, x squared minus 2, not irreducible over rational numbers. It isn't. You can't factor that. But you can write it as x plus the square root of 2 times x minus the square root of 2. Those are irrational conjugates of each other. And they will multiply to be x squared minus 2. The product, the square of those two terms. Irreducible over the rationals, but reducible over the reals. So those are factorable now under real numbers, not under rational numbers, but under real numbers. These are not factorable in any real number. Okay. So that's The slideshow doesn't show example 7, which we just did. It goes directly into this, which is example 8 in our book, but it's example 7 in the slideshow. And this is the current slideshow. For a long time, I used the DVD that was with the previous text, and I thought, well, they just don't have it updated. They don't even have the current one updated. So here's what we've got. Is there time? Okay. So we'll begin next time with example 8. Okay? On page 157. Let me, while we're here, and we are here, give you some homework exercises, because I know you wouldn't like to go into the week with no homework. Okay? Any of the odds, 9 through 13, all those odds are at calcchat.com, 9's at calcview. Either 15 or 17, they're both at calcchat. Any of the odds 19 to 27, they're all at calcchat, 25's at calcview. Okay? Either 29 or 31, they're both at calcchat, 29's at calcview. Either 33 or 35, they're both at calcchat. Have we done the rational zero test? I think so. Either 37 or 39, they're both at calcchat. Now, you don't have to worry with 41 through 45. Those all have complex numbers in them. If you want to play with them, you can. They're fun, okay, but you don't have to. Same with 47 and 49. You don't have to if you don't want to. 43 and 49 are at calcview. And we'll begin next time with factoring the polynomial, so we'll stop there. Just go through 39. Good deal. All right. We'll see you on Thursday. And be working on those quizzes.